Okay, final result from a data plane forwarding point of view, if we go to the customer edges, we should see that they are in a full mesh of layer 2 connectivity. So from router 1's point of view, if we ping the broadcast address, we should see that we get responses in from 7 and 8, which means that they're on the same emulated LAN segment. So if we look at specifically how the pseudo wires are set up, again, we have the service instance that's going from 2 down to 1. 2 is then taking the service instance and putting it as part of the bridge domain. Okay, so the bridge domain includes the service instance, which is going to the physical port, and then it also includes the virtual forwarding instance. This is the one that's going towards router 3. So from router 2, we can see this when we look at the show VFI, and if we look at the show bridge domain. Okay, this is really your final verification, because if you're learning the MAC addresses, then you know that the control plane had to have been built, because you can't learn the MAC addresses in the data plane unless the signaling of the labels and everything was correct. Okay, if we were to have other issues in negotiation, we can see this when we look again at the show MPLS L2 transport virtual circuits and look at the virtual circuit detail. This would tell us, like, do we have problems with the MTU being negotiated? What is the specific label value that we're using for the circuit? And then it should tell us here what the label stack is as well. Okay, so let's look at the full config on all of these for this. Let's say show run section gigabit Ethernet to or bridge or VFI. Okay, so this guy is the UPE, which is basically that. So it's really only a couple commands. It's just that if you didn't memorize this, you want to make sure to know where it is in the documentation. I would say the bigger deal is to make sure that the core transport is working. And then if you can just find where this example is located, change the values around with whatever the question is asking for. And then there's not much that can go wrong with it if the core is working properly. But again, that's assuming like that we could go to router 2 and trace to 4's loopback from our loopback and make sure that we're following a label switch path, or over to router 5. In this case, 2 and 4 are directly connected. So router 2 is the penultimate hop, but we should see over to router 5 that we have at least one hop in the middle, so we have MPLS between them. Okay, then on the NPE, same config here, except there's no attachment circuit because it's only bridging between pseudo wires. And then these ones here are going towards the UPEs. Okay, so it would say split horizon disabled towards UPE, and then split horizon would be enabled towards the NPE. Okay, so this is basically the VPLS legacy syntax. Okay, and I'll save this file and then I'll put it in the file share for you guys as a reference after this. Okay, it's HVPLS syntax example. Okay, so let's now do it in the newer format, which is the one that you can basically just copy from the documentation and then change the values around. So first, let's get rid of the bridge domain and the VFI. So let's say just default interface gig2, no L2 VFI and VPLS. Okay, so let's say show run, pipe section, VFI, or bridge. So 2, and we need to get rid of that one. Okay, globally, no bridge domain 1. So 2, 3, 4, 5, and 6 should all be blank. Okay, so let's look at their example, and I believe that there's the full config example from what they have, which we have the bridge domain. Let's see if it also shows the which is missing what here? They're doing an Xconnect as opposed to a VFI. It basically does the same thing, but there's just multiple syntax formats for this, which is, I don't really know why they do it this way, because it's overly confusing that there's like 4 different ways to do the same config. But it does say in the documentation, in the later releases, this old stuff is going to get deprecated out and it's not going to be there anymore to go to the unified syntax format. But it would basically be the difference between these two. Okay, so in this example here, there's the Xconnect member is either in the virtual forwarding instance or it's under the bridge domain. If it's under the bridge domain, it means it's facing from the NPE to the UPE. If it's under the VFI, it means it's facing towards the NP. It's facing the upstream direction. So basically, split horizon is going to be enabled on this one, and it is going to be disabled on this one. But it's overly confusing from a syntax point of view because it doesn't tell you with that command, is split horizon on or off. Okay, so let's say that we had the same config at the port level. Gig 2, we had service instance 1 that is encapsulation default. Okay, let me make sure that that's the correct syntax. So this would be on 2, 4, and 5. Okay, then we have the virtual forwarding instance. We'll say that this is called HVPLS. VPN identifier needs to match between all of them, and then we're peering towards the network PE. Okay, in this case, 3333. And then under the bridge domain, we're saying that the VFI is a member, and then also the member is gig 2 and service dash, I think it's service dash instance 1. Which that should say HVPLS. Okay, so let's show run section VFI or bridge. Okay, so this same thing, and actually no, that should not be, that's the wrong address on 5. Okay, that should be going towards 6. Okay, this config here should be equal between router 2 and 4 because they're using the same network-facing PE. 2 and 4. Okay, now the difference is going to be from the NPE, is split horizon enabled or disabled? Now, from the syntax point of view, let's say for the sake of argument you don't know which is which, whether their address is supposed to be done in the top portion or the bottom portion. So we know we need to create the bridge domain anyways. The difference is that there's not going to be a physical port that it's associated with because the only thing the core network is doing is bridging between the pseudo wires. So let's say that we're going to put the network PE in the bottom one, and then the user PE in the top. So this is the UPE config. Okay, we're now trying to build the NPE config. So we have the bridge domain and the VFI, the same VPN number because we want to bridge together, and this is from router 3's perspective, so I'm going to say that this is going towards 2222 and 4444. And then the member here is going to be 6666 and cap MPLS. Okay, I believe that's the right syntax. Okay, so this is going on router 3, which is the box in the core, the NPE. Okay, if we now look at the show bridge domain, right now we're not learning any MAC addresses yet, but the important point would be is that if we look at the show VFI, it tells us here, is split horizon on or off? So where we want it enabled is the core to core links, which in our case should be from router 3 to router 6. Router 3 to 6, split horizon is off here. Where facing towards the edge, this is where we want split horizon disabled. It's basically the opposite config. Okay, so I need to undo this and then recreate it. Okay, so let's paste this in twice. to delete it. It's probably going to give an error that we can't delete the bridge domain until we do the VFI or vice versa. So we're going to say that the edge-facing X-connects are under the bridge domain, and then the core one is in the VFI, which it does make kind of sense if you think about where would the physical port be going, because normally the physical port is part of the bridge domain, and in our case, the physical port is this circuit that's going towards the edge. Okay, this goes towards the CE, and then this goes up towards the core of the network. Okay, so 3 is going to say this, and then on router 6, that's going to be facing towards the core, and then this faces towards the edge. Okay, which would be on 6. Okay, so now let's look at on everyone to show VFI. Router 6 says split horizon is off towards the edge, but it's enabled towards the core. Router 3 should say the same thing. Split horizon should be off towards the edge, which is to 2 and 4, but it's enabled towards the core. From the user PE's point of view, split horizon is always going to be on. So if we show VFI, split horizon is on, yes. Okay, same should be true on router 4, and then also on router 5. Okay, if we then look at the MAC address table, let's look at the show bridge domain. Router 5 says, I'm learning dynamically my addresses that are coming from the physical port. Router 4, likewise, is learning towards the physical port. Router 2 is not yet learning anything. So let's say show run interface gig 2, show run section bridge or VFI. That should be fine. Okay, so on router 1, let's ping to the broadcast address. So let's see what are we missing here? Let's start on the user facing interfaces. Okay, next thing I want to look at is, did the pseudo wires actually come up? So we saw in the bridge domain that we were learning our local MAC addresses, but no MAC addresses were associated out the pseudo wires. So we want to look at the show MPLS L2 transport virtual circuits. It says the VC status is up. Okay, this is the one that's going from router 2 over to router 3. Okay, so in total we should have 1, 2, 3, 4 circuits. Okay, so 2 to 3 is up. Let's look at the VC detail. MTU is the same. We did get labels associated with them. And it says that the VC status is up. Let's look at router 3, do the same thing. Show MPLS L2 transport virtual circuit. Circuits are up. Okay, from router 3's perspective, we have 1, 2, 3 circuits. On 6, show MPLS L2 VPN or L2 transport VC. Circuits are up. Okay, same thing on 4 and 5. Oh, you know what I did? Why this is not working? I defaulted gig 2, but I sent that command to everybody. I sent it to the edge routers as well, the customer edges. So on router 1, 7, and 8, I deleted their IP addresses. That's what's wrong. Okay, let's show run interface gig 2. Okay, router 1 on gig 2 was the IP address 10.0.0.1. Router 7 was 10.0.0.7. And router 8 was 10.0.0.8. Okay, so let's ping the broadcast address, and hopefully we should get a response from 1 and 7, okay, which we do. So again, in the core, if we look at the show bridge domain, the user-facing PE is learning the MAC addresses from the physical attachment circuit, which in this case is service instance 1 on the gig 2 interface, and then also learning MAC addresses towards the core over the pseudo wires. We're then bridging the traffic over to router 3. So if we go over to router 3 and look at the show bridge domain, we're learning the MAC addresses, but in this case, they're coming in only the pseudo wire, so they're going pseudo wire to pseudo wire. And then this is going down to the edge, which is going to go towards router 4. So let's say show bridge domain. Okay, there was a question here, why do we need to enable split horizon on the user-facing PEs? Because, well, technically it would only matter if the UPE is multi-homed to multiple NPEs. Okay, so let's say that the network looks like this. So in the core, we have 1, 2, 3, 4 network-facing PEs. Okay, these guys have a full mesh of connectivity. So we'll say this is N1, N2, N3, and N4. Okay, hopefully this is kind of self-explanatory why split horizon needs to be on here, because the problem is that if the broadcast packet goes this way, we need to make sure to not send it back out these other circuits, otherwise it's going to loop around infinitely. Okay, so split horizon, yes, we want it enabled there. Okay, then we go from the NPE towards the UPE. Okay, so let's say that this is U2, this is U1, and then over here we have U3, but this one is multi-homed to both of these. Okay, then we're going to the customer edge. Okay, so CE1, CE2, and CE3. Okay, now a broadcast comes in. Broadcast comes in from customer edge 1, it goes to user PE1. This guy says, yes, it can come in the attachment circuit, it can go out the pseudo wire. So it goes to N1. N1 is going to say, yes, since it's coming in from the user PE, and split horizon was disabled, so no split horizon there, it means that we can send it to the other network-facing PEs. Okay, so now the frame gets flooded this way, and this way. From N2, 3, and 4, split horizon is enabled, so they cannot send it back towards each other, but they can send it towards the user PEs because split horizon is off. Okay, so now it goes this direction, split horizon off, both that way. Now from U3's point of view, it needs to figure out, when I receive the broadcast in the pseudo wire, do I send it out the other pseudo wires or just towards the attachment circuit, just towards the physical customer? The problem would be here is that if it came in this direction and then went out that direction, it's going to cause a loop. Now, it's not going to cause an infinite loop in this case, but it will, or actually no, it will cause an infinite loop, because from N4's point of view, split horizon is disabled on the links that are going to, or on the pseudo wires, I should say, that are going to U3. So basically, we would have the case where it comes in here, comes back, and then goes this way, and then back around. If we were to disable split horizon from this guy's pseudo wire pointing that way. So it's unidirectional, which is really the key here, is that U3 says going this way and this way, yes, split horizon is on. And then towards the customer edge, that doesn't really matter because the split horizon is only an issue between the pseudo wires. Does that make sense? Okay, there's another question here. So the bridge domain is connected to all the neighbors in the VFI config. Yes. So the bridge domain, you need to configure on all of them because that's what the MAC address table is. It's like saying VLAN 10 on a Ethernet switch. So it's a lot of config for a large network. Yes, this is one of the main problems with VPLS is that it's hard to scale operationally, because every time you add new circuits, you have to update the configs, or add new PEs, I should say. You need to update the configs for whatever that new VPLS that you're creating. In practical implementations, though, it's normally scripted anyways, so it goes through some sort of like provisioning system that does the config. But if you show run on these core boxes, there's tons and tons of circuits that they have manually provisioned. Okay, so again, where you can find that example from the documentation is under iOS XE, and then down under the config guides, somewhere hidden down here. MPLS label switching, layer 2 VPN, and then either under HVPLS with MPLS access or just configuring virtual private LAN services. There's a question, can we use BGP like we did yesterday with just VPLS? That I'm not 100% sure of, because the issue would be that once you create the dynamic association of the pseudo wires, you would still need to disable split horizon on them but you can do a combination of both of them. So I think what you would be able to do would be to say on the UPEs that we're going to use BGP in order to discover what are the NPEs, and then the NPEs we could use BGP to discover what are the other NPEs. Okay, so let's say we had a full mesh between all of these. But then the one that is going from the NPE to the UPE, we would have to manually configure that in order to manually disable split horizon on it. Now, I haven't tried the config, but I don't see a reason theoretically why it shouldn't work, because the labels are still signaled through LDP. Okay, which reminds me, I want to show what does this look like in the data plane now. Okay, so let's say that we're going to send a frame from 8 to 7. So let's take a look at our packet capture. Okay, I'm capturing in this case just ICMP packets, and let's go to router 8, and we're going to do just one single ping to 7777, source is 8888, and repeat is just one packet. Okay, so there's 3 hops that it was capturing here in the virtual switch. So the first hop, I believe, is going to be from 5 to 6, and then second hop is going to be from 6 to 3. Third hop is going to be from 3 to 4, and then it's going out the attachment circuit. Okay, so first one we captured here should have been in from router 5. Okay, it says that there is a 1 label stack on the frame, so it's Ethernet, and then we have MPLS inside there. Then we have the pseudo-wire control word, then the inner Ethernet frame. Okay, so what we're tunneling is basically this portion here. Okay, this is the these two together. This is the VPLS header, and then this is the underlying transport of the core. Okay, so the VPLS header in this case is just 1 label, but this is just because these boxes are directly connected. If we had other routers somewhere multiple hops away, then we would have multiple interfaces that we'd have to go through. And actually, we should be able to show that here. If I were to disable, let's disable, let's say, the link from 5 to 6, and then the traffic should route through XR1. And let me make sure XR1 actually has this correct config. Show IP interface brief, which right now it doesn't. Okay, so let me do a commit replace. And this topology here, the initial configs are in the workbook section under the L2 VPN, and they're also in the shared files here attached in the upper right of the classroom window. So let me get to the initial configs for L2 VPN for XR1. Okay, so for the core routing config, it just says OSPF on everywhere, and then LDP auto config. So between 5 and 6, let's shut down gig1.56. Okay, so 8 should still be able to reach 7. It's going to take a minute for it to reconverge, though. Okay, which we can reach it. So now let's restart the capture, and then we'll ping again just with 1 packet. Okay, so we should have an additional hop now. Okay, first hop is where it's coming in from the user-facing PE, which in this case is router 5. Router 5 should be adding the pseudo-wire label, which is coming from targeted LDP, and then it's adding the transport label, which is coming from regular LDP plus IGP in the core. So first packet here should have a 2-label stack. We see label number 23 and label number 26. So again, this one here is the VPLS label. Okay, that's the one that came from targeted LDP. And then this one here is the core transport label, the one that came from IGP plus LDP. So let's look at router 5 specifically and look at where did it learn these from. So on 5, if we look at the show MPLS forwarding table, label number 23 is going to be talking about who? Okay, who's the destination of the layer 2 tunnel? Let's look at the show VFI. Destination is router 6. So if we look at the show MPLS forwarding table and we look at transport label number 23, this is the one that's getting us towards router 6. So you can think of this kind of like our L3 VPN examples where we were doing inter-AS option C. And every time you change the next hop value of the BGP VPN v4 route, we were changing the tunnel destination. In the case here with hierarchical VPLS, every time that we change the pseudo-wire destination, that's where we're changing the label. So 5's tunnel terminates on 6, 6's tunnel terminates on 3, 3's tunnel terminates on 4. So the label is going to be changing 3 times in the VPN label. Okay, the bottom label is 26. If we look at the show L2, show MPLS L2 transport virtual circuit detail, this says that the local label is number 26. Okay, this is the one that router 6 allocated towards us. Okay, we go one hop further, and the next packet is this one here. Okay, this guy has just one label. Okay, it's got just number 26. So if we go over to router 6 and we look at the show VFI, this is going to be the circuit that's going towards router 5. If we look at the show MPLS L2 transport virtual circuit detail, and we're looking specifically for 5555, we should see that label number 26 was the one that was allocated from router 5. Okay, it happens to be the same number, but it's technically 2 different labels. It's being reallocated from 5 to 6, or excuse me, from 6 to 3, this should be. Or no, let me think about this. This is going from 6 to, yeah, 6 to 3. So I should have said begin 3333. Which it is saying local label is 25, remote label is 30. Let me make sure I'm looking at the right portion of the packet. Okay, so it says 23, 26, then just 26, then 30. This is the one, okay, so this is the one that's going towards router 3, and then it's going towards router 4, and then router 4 is going to send it out to the destination. So notice that the underlying label is changing, which is the key, because there's multiple circuits. In the case of a regular VPLS, it would just be one label switch path end to end, because the PEs are directly forming a full mesh between each other. Okay, questions on this example here with the hierarchical VPLS? There's a question, is there anything interesting with the pseudo-wire control word? The control word came from the non-Ethernet encapsulations when you needed to encode things like the ATM cell loss priority, or the frame relay discard eligibility, or the beckon and feckon congestion notifications. I'm not 100% sure if it's actually used for anything inside the VPLS header, but it is still listed there. Where this would actually show this would be the RFC for it that shows the packet format. So this would be number, where was it? 4762, VPLS with LDP. RFC 40, which one was it? 4762. VPLS using LDP signaling. So let's look at the frame format. The control. Well, this just shows the signaling. So it may be using probably the previous format, which is this one, 4906. 4906. Transport a layer 2 frames over MPLS. Okay, it says label mapping says that if C equals 1, you must have a control word. If C is 0, you must not. But what is this specifically encoding? To tell you the truth, I'm not 100% sure where this would be listed, what the actual format of it is. But if we look in the packet capture, I believe that the control word is empty, because there's nothing that we actually need to encode. Sequence number 0. So it's there anyways. It's just that in the case of Ethernet over MPLS, it's not really needed. For the legacy encapsulations, yes, it is, because it encodes stuff that was lost from the layer 2 header.